simplest, well, one of the simplest examples of the application of this Bootstrap philosophy to try to classify 4-point functions in de Sitter space, trying to follow the inspiration coming from this flat space example, this simple example. It illustrates the power of these ideas. So this is relatively new, but also relatively old now. And since then, there has been quite a few developments. And I'm just going to give you some references if you want to see what happened since then. We wrote a review for this snowmass process in the US. And, of course, I didn't write the archive number. So one is called the cosmological bootstrap. And the other, these are the two papers that I was involved with, so I'm just mentioning them so you can, depending on your interest, you can learn more stuff about the topic of these lectures. And the other is called Inflation. Theory and Observations. Yeah, this was particularly interesting because you need to make many people happy. This is more closely related to the lecture now, and this touches more on the prospects for us potentially detecting new physics from the early universe, as well as theoretical developments to both compute and predict and decode these signals. So I'm mentioning all of this because in the first hour I'm going to walk you through a simple example, and then I'm going to jump to like today. Okay, so the last lecture is going to be like a research seminar kind of thing, because yeah, I'm just excited about it, so I want to share it with you. It's probably not going to be very pedagogical, so apologies for that, but I hope you'll get some of the excitements of some new stuff. Okay, don't worry, it's not completely decoupled. It's if you wish, I'll motivate. So very good. So this is where we're going today. So okay, so we want to understand if there is an analogous construction for the case of 4-point functions. We would like to compute the 4-point function in the case that this is a generic mass and spin particle here, and then we want the external legs to be very light to leave an imprint at late times. So in particular, we're interested when the external mass is 0. And most interesting cases are spin 0 and 2, the scalar and the graviton. We skip spin 1 because famously gauge fields have conformal symmetry, so they are not produced copiously during inflation. So spin 1 massless fields behave more like massive scalars. So that's why we only talk about scalars and gravitons. Okay, J external, not to be confused with the internal J. The internal J can be anything, and of course this signal is only going to be very interesting if m is smaller than some number, or the h bigger than 0. But we're going to consider generic m just as a mathematical physics exercise. So there will be a couple of steps. So first step is we're going to study contact interactions, but of fields of mass squared equals 2h squared. So this is conformally coupled. It's just much simpler. I'm going to call them var phi. Just because the mode functions, the phi classical, are plane waves essentially, eta to the ik eta. Okay, the mode function of a massless field modulo normalization. I'm throwing away factors of h and square root of. So it's a little bit different. In particular, notice that at late times as eta goes to 0, this goes to 0. So in principle, there's no signal, but a la ADS CFT, we strip out the decay rate, the slowest decaying rates of the signal, and look at the resulting profile. Okay. So we want to classify contact terms first. Then second, we're going to look at scalar exchange, so m and j equals 0. And this will satisfy a differential equation. In the boundary momenta. So instead of solving for explicit time evolution, we're going to show that these objects, I can act on the boundary, just move around the points, and it will satisfy an interesting equation that encodes consistent time evolution. So the baby version of holography for this particular diagram. Okay? And then the last step is kinematics. So the Sitter symmetry is so powerful that if I understand this diagram, I can land in the diagram of interest just from kinematics. So there will be some operator, O, acting on the diagram that we computed, and generic mass, spin equals 0, with m squared equals 2h squared. That's going to give me whatever we want for m squared equals 0. Okay? So this is the power of kinematics. Very good. So this is the plan. I'm sure I'm not going to make it, but well, at least you know what I'm striving to do. And keep in mind that the star of the story is the existence of a differential equation, which is a bit surprising. In one hand, it's surprising that you can act externally at the boundary here, only moving around the momenta, and encode time evolution. On the other hand, it should not be surprising to you, because remember that all the dynamics is encoded in this equation, k eta star equals 1, right? So for any external momentum, if I change the external momentum, the physics becomes dominated by a certain range of conformal times, right? So that's why if I move around the momenta, I'm essentially kind of dialing up and down the times in which this diagram gives the most dominant contribution to the signal. So this is playing the role of you know, like probing the bulk of space-time. All right. So enough with the intuition. Let's. Are there any questions? Or okay. So first thing, context diagrams. So first of all, let's do simplest possible example, lambda phi to the 4 for m squared equals to 2h squared. And I'm going to compute the wave function. I think I'm going to compute the wave function of the universe. So I'm essentially just evaluating the action on shell. Okay. So this is going to be equal to integral over conformal time. There's only one conformal time where interesting interactions happen. So there will be each of the mode functions, and the lambda here, each of the mode functions gives me eta to the 4, e to the I, k1 plus k2. But then the measure has 1 over eta to the 4th. So it's conformal, right? So you would say, well, why is it? It's just like flat space. It's exactly like flat space. In particular, there is times delta function, but now there's only translation invariance. If I could do the time integral from minus to plus infinity, I would get a delta function of energy conservation, right? Because these are massless particles. They would look identical to the computation in flat space. But now conformal time runs from minus infinity to 0 in de Sitter. Okay? Therefore, this is the answer. Lambda over. All right. So this is the answer. So it's almost like the flat space answer. And notice that there's something new already. In that, if you look in that formula, the contact interactions are analytic functions of the kinematics. While this formula here has a singularity. It's not singular in the physical region because I'm just adding up absolute values of momenta. So ki, a bit of notation, is the absolute value of the momentum, which has a square root branch cut, right? So in the sense of like analytic functions, I can consider changing sheets and making these k's negative. Therefore, I can access the, let me call this thing, in analogy with flat space, let me call this thing E total. Okay? So, I can access E total going to 0 in the sense of analytic continuation. The signal is completely smooth, not singular in the physical sheets, but I can take these limits. And then in these limits, the non-Gaussianity becomes singular. But interestingly enough, oh, by the way, confused about something. Okay. The wave function, as E total goes to 0, or the wave function coefficient, if you wish. Let me call it phi 4. Okay. It's a bit of a misnomer because I'm computing the wave function coefficients, but in any case, as E total goes to 0, it becomes singular. So it's 1 over E total times lambda. But lambda is the flat space scattering amplitude for lambda phi to the 4th. Okay? So this, this is a trivial example, but it's a general phenomenon. So the claim, and it's easy to understand why. If I look, okay, I know what's going on. There, yeah. Why am I staring at the board? What's the problem?
Is it the integral convex exponential?
No, this is fine with the I epsilon. No, I was shocked because there is signal. No, I'm shocked because there is signal. It should decay, right? It should decay. Should go. It's because there's some normalization here in the propagation. Anyway, it should be 0 at late times, the signal. So there's some eta 0 to the fourth here when I put some eta 0. Anyway, it's coming from the normalization of the propagators. It doesn't matter. So again, in the sense of ADS CFT, I'm always looking at the signal, the true signal, the function, the 4-point function will go like eta naught to the 4. So when I send eta to 0, it's literally 0, but then I look at the leftover that depends on the momenta, okay? So this is what I'm focusing on. It's just that in that particular example, I wasn't seeing where it was coming from, but it doesn't matter. Okay, but so here it appeared in a trivial example, but then I claim that it's a general phenomenon. So if I take any correlator, K1, K2, K3, K4, there will always be these time integrals, and I can always, like, I don't know, move to the center of mass frame, or whatever it means in time, the intermediate time frame. So there will be one time integral that will always have the sum of all the external energies. And now if you look here, if I send the total energy to 0, then even with I epsilon prescription, this integral that was getting damped at very early times starts to peak there. So that's why the signal, that's why the non-Gaussian becomes singular. And physics is dominated by very early times, when all the modes were very short, probing very short distances, very sub-horizon. Therefore, they shouldn't even know that they're in curved space. Okay, so that's the intuition. So when I send E total to 0, this should go like E total to a certain power. It's typically singular. It can be logarithmic, the singularity, and so on, times the flat space scattering amplitude at the high energy limits, okay? So let me put some brackets, which mean at high energy. So for example, if I had massive exchanges and so on inside of the diagram, I would have to send the internal energies to infinity also. So it washes out internal spectroscopic data of what's going on. But it's like the high energy limits of the scattering amplitude that gives rise to the same process. So this should give you pause and should make you hopeful that all the magic that you're seeing in the other lectures on flat space scattering should have some avatar in cosmology, because this object is a different object. You calculate something different, but in its analytic structure, it should contain the magic of flat space scattering amplitudes. So this is a nice result. And it will guide us towards constructing these correlators. So just like, to make the parallel with the formula that I'm erasing right now, context diagrams have the simplest analytic structure. They are smooth in momenta. And context diagrams in cosmology, in the sitter, they are not smooth, but they have only the singularity, because there's only one time integral, right? So there's only one time integral. So any context diagram can have, at most, in the denominator, it can have this E total singularity. And it must be compatible with the sitter kinematics. So that's all you need to classify everything. So any context diagram must be of the form numerator in the momenta divided by E total to a certain power. Okay? you can change the power, and then you have to change the power of the momenta in the numerator to comply with scale covariance, right? Remember that the de Sitter metric has this rescaling symmetry, which means that the correlators are homogeneous functions of the momenta of specific weight. So if I increase the power of E total, I must compensate in the numerators, and the numerators must be compatible with de Sitter invariance. In other words, if I hit it with the generators of de Sitter boosts, the non-trivial isometries, they are hard to see in the flat slicing metric, it should impose some constraints in the numerator. So now you know your strategy. You write down any numerator of the right weight with Bose's symmetry and so on. At any power of E total, there are only so many things that you can write down, and then you impose that it's annihilated by a differential operator. So you'll find that the coefficients are related to each other. And then you classified everything. Okay? So that's it. So you're done with the first part of the formula that I shouldn't have erased. So with this, we accomplished this part of the flat space. Okay, so let me, yeah.
Once again, there was a comment that you made about the connection with the flat space amplitude, because is it for high momentum, these guys are not able to distinguish, they're not sensible to curvature, so there's some notion of connection to flat space?
Because in this limit, you're probing very short distance physics, so it is flat space physics, but flat space physics at very short distance, so very high energies.
So that's the thing I'm confused with. In the hypothesis, we are setting the total energy to be zero, so we are continuing, the momentum in such a way that we get, and at the same time, we also assume that each individual momentum is very high. So there are two hypotheses here I'm using. Not only because, the sum of the energies can be zero in different ways. Each individual momentum should not, be
yes.
large as well.
No. I'm not sending the individual momenta to be large. I'm just saying that the resulting formula here will match a flat space scattering process in which I make the external four momenta to be large. But it's not like I'm dialing the three momenta to be large by.
So maybe I'm understanding something. So if the external momentum are all of them large, and I do this limit, then the amplitude resembles.
No, the external momenta can be whatever you want. The only thing you need to do is send the total energy to zero. Then the claim is that because the integral peaks at very early times, it will match another thing, a flat space scattering process, in which in that flat space scattering process you send the external energies to infinity.
So then maybe I'm understanding the equation in the sense of like high momentum, short time, then it seems like flat space. Maybe it's early times, no expansion. Maybe,
here, the integral peaks at very early times.
Yeah, this understands it. Yeah.
Right. So then all the modes are probing very short distance dynamics. But then yeah. So that's why it matches the flat space computation.
Yeah. So being not aware that there's some expansion, some. Since it's very early time, there is no time for curve.
Yeah.
Okay, I see.
So all the interactions happen at such short distances. The modes barely know they're in curved space, and then they're pulled apart by the expansion of space-time.
Okay, thanks a lot.
Okay, sure. All right, so this is, so let me just give you an example, because then I can, it's not going to classify all possible numerators, but it gives you some idea of how to proceed. So if I take the 4-point function, and let's assume that I'm focusing on exchange diagram. So there's a natural separation between the momenta on the left and the momenta on the right. So I'm going to propose an ansatz that is tailor-made to understand this type of diagrams. Okay, so the exchange momentum I'm going to call S, not to be confused with Mandelstam S. Maybe I should put S flat here. This has different dimension. This is just a 3 momentum, okay? But in analogy with S channel, this is just K1 plus K2. And I remind you, if I remove an arrow, I'm taking the absolute value of a momentum. So now you consider the following ansatz. You take a function. Naively, it would be a function of all the 4 momenta. But because of scaling symmetry, I can write an ansatz like this. Okay. So the 1 over s takes into account the scaling weights of this 4-point function. So the delta function takes into account spatial translations. There are only mods of momenta, so it takes care of rotations. So I diagonalized up to now 7 isometries. There are 3 special conformal transformations, 3 boosts left to do. And well, this is an exercise if you wish, but you have to put it on the computer. It's not trivial to check. That this ansatz diagonalizes 2 out of the 3 boosts. So it almost does the job of diagonalizing everything. And then the last boost imposes a differential equation on this function. Okay? So this ansatz is tailor-made. Notice in particular that I could have, I have 4 momenta, I have 12 pieces of kinematics, and if I impose translations and rotations, I should end up with a 6-dimensional kinematic space, right? And, right, so I'm not, I'm using just 5 variables, K1, K2, K3, K4, and S. So one of the variables I threw away, it's like T, if you wish. This variable for this particular process will only appear if I have spin. Okay, so this ansatz is tailor-made for scalar exchange. So okay, just to make life simpler. So I'm assuming that it's independent of this extra variable here. And now let me call it U and V in analogy with, it's not really a cross ratio, but in analogy with cross ratios. In conformal field theory, we call them U and V. And then the last boost implies that F satisfies this differential equation, delta U F equals delta V F, for which delta U is the second order differential operator. Okay? So it's the result of a calculation. It's not, if you're confused of where it came from, don't worry. I'm just imposing that it's invariant under boosts. Okay? And then after some work on the computer, you get here. For example, if I take this simplest example, 1 over E total, lambda over E total. This is an example. In this notation, I would have to pull 1 over S. So it would be lambda over S, S over E total, which in these variables here would be lambda over S UV divided by U plus V. Okay? And if you are on your computer board, you can pull up Mathematica and check that it satisfies this equation. Okay, so this happens to satisfy delta U minus delta V. But now, wait a second. This is a second order differential operator, let me hit only delta U on this UV over U plus V. So what will happen? I'll end up with a formula. It has 2 derivatives, so I'm going to generate U plus V cubed. Agree? Times some numerator. But clearly, it must solve the constraint also, right? In other words, consider delta U acting on UV over U plus V. This is some formula. Well, delta U minus delta V times delta U I mean, delta U commutes with itself, and of course it commutes with delta V. So I can just pull the delta U equals delta U times this acting on. So okay, so this is another solution. So I just discovered another contact interaction. It's going to be higher power of E total, so it's going to be 1 over E total cubed times some numerator. Okay? If you try to send E total to 0, yeah, then you can really do it on Mathematica if you want to play with this. If you send E total to 0 of this numerator, here's what's going to happen. It's going to asymptote to the following expression, minus, and let me restore the absolute values in order not to create confusion. K1 plus K2 squared plus K1 plus K2 squared. Now look at this. Let's take the 3 momentum, K1, take its absolute value, this, and call this object P1 mu. So what is this? It's P1 mu, P2 mu, which is the S flats. And then you can check at higher. If you so that's the strategy. So if you want to generate, it's clearly going to generate all positive powers of the Mandelstam S. Okay. When you integrate out a very heavy scalar particle, in the S channel, it only generates powers of the Mandelstam S. Okay, it doesn't generate powers of the Mandelstam T. So that's the strategy. To generate all contacts, interactions that are like powers of S, you just take delta U to the n, action UV over U plus V. Okay? So that's it. So very simple. You don't need to do any Lagrangian. So that's all I have for contact diagrams. The important thing to remember is they have a very simple singularity structure, only E total. Now let's do exchange diagrams.
And for high spin,
For-
what do I get from the scalar to the AJ?
For higher speed, remember the strategy for now, okay, so there are 2 ways. One is you forget all I said about the ansatz. Forget about these ansatz. Just try to write down the most general polynomial in all of the momenta in terms of the 6 variables, the k's, s, and t, with the right weight for a given value of E total, and then impose that it's boosting variant. So then order by order, you find relations among the coefficients, and you find everything. And then when you send E total to 0, you will discover powers of S times powers of T.
Right, but you said that if you understand this one, you can actually reconstruct one for IJ, right?
Yes. So right now, our strategy is to just focus on scalars being exchanged. And then once we understand that, then I claim that I understand spin exchange. So if you take, if you apply the ansatz that would raise the spin of the exchanged particle to this function here, you're going to naturally generate powers of T. When you apply this to contact diagrams, you're going to generate the other Mandelstams, S to the N, T to the M, and so on. So the ansatz is applicable regardless of whether there is exchange or there isn't. So it will also work for context terms.
Question?
Yes.
You got our channels, right? Contributing free level. You got the T and U channels still when you
Yes.
do the diagrams slightly agree to just one. Is it clear that when you boost invariance is only on the whole amplitudes with all 3 channels, right?
Well, you can
expect that only one of the diagram is
for scalars you can always engineer scalars that have a selection rule where only the S channel contributes.
okay.
The moment you talk about spinning external particles, what you said is absolutely right, and you can't just focus on the S channel. There will be breaking of boosts, and this is crucial. This is, I said, oh, you can get any diagram you want. You can say, well, let's just keep working on the S channel, and let's try to raise the spin of the external particle and consider graviton exchange. Then naively the formalism works, but then when you go and try to check boost invariance, you'll find that there's a very subtle breaking. And the only way to fix it is to add other diagrams. Not only that, you need to tune the couplings, and then you discover the equivalence principle. So all of these things follow, but then for external scalars, it's not an issue. Yeah, for external scalars, you can exchange a massless spin 17 particle. There's no problem. The problem is when you put it on the outside. Okay. Exchange. So first of all, I'm doing massive exchange, spin 0. And remember that these objects must satisfy the kinematical constraints delta U minus delta V equals 0. And well, let's look at delta U. It doesn't have the U plus V equals 0 singularity. So nothing special seems to happen when you send U to V, U to minus V, sorry. It doesn't seem that it does anything to this particular equation. So this is just a kinematical constraint, and dynamics must come in. There must be a subset of solutions to this equation that corresponds to this dynamical process, okay? But notice that it has other singularities. Let's look at the other potential singularities. There are singularities at U equals 0 and U equals plus or minus 1. Just looking at when the top derivative becomes, the coefficient of the top derivative goes to 0. So U going to 0 is when S goes to 0, okay? So when S goes to 0, it means that you're giving very low momentum for the exchanged particle. So then you're allowing it to travel very long distances, okay? So this is the limit in which you should see particle production explicitly. So this is a singularity that is desirable. It should be there in the diagram, okay? Now U going to plus or minus 1, let's see what it means. It's S over K1 plus K2 going to plus or minus 1. So it's S minus plus. So when S minus K1 plus K2 goes to 0, it just means that you're aligning two of the momenta. For example, something like this. Nothing special should happen here. Okay? It's just taking two momenta to be collinear. Nothing is becoming soft. There's no issue. It's just scalar particles. There should be nothing special. If you stare at the integrals, there is nothing funny going on. So there should be no singularity. As S minus K1 plus K2 goes to 0. So this is important to keep in mind because the kinematical constraint seems to tell you that generically you will have a singularity there. But you don't want a singularity, and this is a physical input. Okay? So this is a physical input. It's related to the vacuum choice. Remember there was a question about alpha vacua, right, a couple of days ago, like a disquantization where you pick positive and negative frequencies and so on. So typically what will happen if you try to do the time integrals and include some regulator and so on, is you will find that the signal becomes very large in this limit. So the existence of the singularity is pointing to you that maybe you could have chosen this type of alpha vacua, the vacua that at short distances don't match flat space, the flat space vacuum. Okay, So if we're going to use Bunch-Davies like simple vacuum conditions, then the singularity should not be there. So it's a physics input. So we'll use it as a boundary condition.
You don't have collinear singularities because you're doing some scalar correlators, is that?
Yeah. Yeah, if you don't know anything about collinear singularities, you just stare at the time integrals, you'll see that there's nothing special happening in these limits. No integrals becoming singular. And on the other hand, there's this singularity, S plus K1 plus K2 going to 0. And now this is more interesting. This is K1, K2, and S. Notice that all the energies entering this vertex are the ones appearing in this sum. So the sum of energies, so let's call it E left, okay? The total energy on the left vertex is going to 0 in these limits. So then the same intuition that I was giving you about probing flat space physics and so on will apply, but only to part of the diagram. Okay? So it means that there will be, in the time integrals, there will be a time integral over only this time on the left, and you will have e to the I, e left, eta 1 times integral d eta 2, etc. Okay? So again, the integral will be dominated by very early times, but only on eta 1. So in this limit, something funny happens, which I'm not going to do true justice to it because it becomes a little bit technical. But so I'll make a cartoon. If you know this, you know that it's not quite true. It's impressionistic, okay? So in this limit, the diagram sort of factorizes. In this limit, what happens is you get 1 over, you get 1 over E left to a certain power times, on the left-hand side, it sort of factorizes. There will be a 1 over S here, the exchange momentum. There will be a scattering amplitude of the left diagram. Times, well, let me put the 1 over S. Yeah, I like the 1 over S here, okay? Let me put a times here with a little bubble just to protect myself from you claiming that I'm inaccurate. So this times is like not exactly multiplication. You need to do something to the diagram. Times the cosmological correlator on the right. But now this lag goes all the way to the boundary. Okay? Maybe let me color code so that it's clear. And the scattering amplitude here will be the scattering amplitude of the scalars going into the massive particle. But now I've got some good news for you. The 3-point correlators and 3-point scattering amplitudes are completely fixed by kinematics. We are in maximally symmetric spacetimes. This is in flat space, this is in de Sitter space. So it means that I have, and this is all dynamical inputs, and these are the only singularities that the diagram should have. You see, if you look at the diagram, what are the possible singularities? There will be a singularity when I send now this left energy to 0. Of course, there will be an analogous singularity when I send the right energies to 0. It's coming from the delta V operator. And I must have the eTotal singularity, which is when I send the external energies to 0 and I zoom into the high energy limit of the whole process. Okay? So it's it seems like an overly constrained problem. I need to find a solution of the kinematical constraint that has only these singularities, okay, and is compatible with these factorization rules and so on. Okay. After some relatively long story, when the dust settles, And then if you want to see the details, you can take a look at either this review or some of the original papers. There will be like a happy miracle. So after everything is said and done, there will be a particular solution of the kinematical constraint that is compatible with all these rules. And here it is, delta U plus m over h squared minus 2. Remember our old friend, the minus 2, the tachyonic story, times f. And here is the E total singularity source. It appears as a source in the differential equation, which was the only extra singularity that I was allowed to put. So this is great because now, instead of having to solve some nasty partial differential equation, which I know very little about what's going on, I am back to 18th century mathematics. I have to solve ordinary differential equations. It won't be entirely trivial because I have to do matching, right? I find a solution of the U equation. There will be some free coefficients, and I have to ensure that it also solves the V equation. But it's not terribly complicated, and you just can beat it to death with like very old-fashioned mathematics. You can find as accurate a profile as you wish at any value of kinematics. And you must do gluing because you have power series solutions, and blah blah blah, and so on.
The solution will be like the sum of all these Feynman diagrams, I guess.
No, the solution is this Feynman diagram. Just one exchange. Then you must sum over other channels if you want.
So you like find differential equations for like the sum over Feynman diagrams.
Yeah, that would be nice, but we don't know how to do that. So if you take, for example, spinning correlator, which the channels must conspire, you can't just focus on S channel. We don't know how to bootstrap the whole answer or find a differential equation for the whole answer. We do it diagram by diagram. Okay, so it has all the singularities. It has the U and V singularities that we like. And so these will serve as boundary conditions. So boundary condition number 1 is the vacuum choice. Boundary condition number 2 is this factorization condition. So then I have 2 boundary conditions on U, 2 boundary conditions on V. It has the E total singularity coming from this U plus V going to 0, okay? And here is the input, the dynamical input of the mass of the exchange particle. Notice that a few comments, if I subtract both equations, you get delta U minus delta V equals 0. So it is kinematically allowed. Another comment that, remember that I was arguing that a few minutes ago that if I take delta U applied on this object, and I applied n times, it's roughly related to the Mandelstam, right? As E total goes to 0, right? So it's like 1 over E total to a certain power times S flat to the n in the limit. So now we're trying to describe the exchange diagram. So what is the exchange diagram for scalars? It's just G squared over S flat minus M squared, right? In particular, let's take the case in which the mass is very large, so we can expand the mass. Right? I can do a low energy expansion of the exchange diagram. I'm just taking S flat to be much less than M squared. So can we see the same thing here? So you're a first year undergrad, I tell you solve the differential equation. You said very easy, F equals 1 over delta U plus M over H squared minus 2, acting on UV over U plus V. What's the problem, right? So this doesn't quite make sense, but to give you an idea, let's make the mass be very large so that we can, again, probe something like effective field theory. So I'm going to drop the 2, H over M squared UV over U plus V, plus maybe minus H over M. So this, remember, delta U hitting the context term are like analog of higher Mundell's terms. So this is how you see in the large mass limits, you see that the solution to the equation will be very similar to like some effective field theory approximation to the exchange diagram. The key difference is that here there are 0 modes. Okay? The 0 modes are related to the homogeneous pieces that you must add to ensure the boundary conditions. It's somewhat related to the fact that you must put an I0 here, okay, I epsilon. So the I epsilon prescription is translated here to the fact that this has homogeneous pieces. So the vacuum choice and so on is encoded in the homogeneous stuff that you must add. In fact, you even find that there must be some non-perturbative piece in H over M that you must add to ensure all the boundary conditions, which is the spontaneous particle production part, the Schwinger effect, Hawking effects type of physics that you can't just access by integrating out heavy physics. Okay? So all of this stuff comes out from analyzing the differential equation in detail.
Just computing the diagram by hand wouldn't give you that piece?
You mean by doing the time integrals?
Yeah, just doing the...
I invite you to try. That's part of the reason why we developed this machinery is because it's hard to do the time integrals. The time integrals, the mode functions are Hankel functions. So I have the eta 1, the eta 2 powers of eta, and then the bulk-to-bulk propagator involves Hankel functions, theta functions, blah, blah, and nobody knew how to compute it analytically. So it's a bit like, it's exactly like in flat space scattering amplitudes when you want to do loop integrals. You trade the loop integration by a differential equation. So that's what this is doing. You can, one way, more lowbrow way of arguing for the existence of this equation is that if you apply it to the time integrals, you see that this delta U commutes with part of the integrand, and it generates the Klein-Gordon operator inside of the bulk-to-bulk. So it hits the bulk-to-bulk propagator, collapses the bulk-to-bulk propagator, and that's why you end up with a context diagram. So that's a simpler way of arguing for the existence of the integral, which would make someone skeptical that this is a general story, because it's very intricately tied to the physics of the Sitter space, the fact that this is possible.
You said it's related to the diagonalizing the last boost, but is there any interpretation for this delta U operator in terms of, I don't know, possible some like dual VCFT interpretation, possible? Because usually when you have a correlator which is annihilated by some differential operator, maybe some non-state condition that you have a null vector in your theory in the spectrum.
No, I think this is just our inability to diagonalize all the isometries. If you had written, so in fact, Costas Kender is here, has written a formula in momentum space that diagonalizes everything. It's just that this ansatz is very useful to tackle S-channel exchanges, but then it fails to diagonalize all of the isometries. You could have, this is a hypergeometric operator, so you could have said that the solution is written by, some Fourier series, but then instead of plane waves, you put in hypergeometric functions. But and in some sense, this is what, for example, Slates and Tarona are doing to solve for these diagrams. Okay, so it is a possible idea to, and it's fruitful. They managed to do it, but yeah. This ansatz just makes it a bit cleaner, the connection to flat space scattering. That's why we used it. Okay. The last thing I want to say before we go on the break. Maybe I should just show you a plot. It's not surprising given what you already learned about the phenomenology, but the resulting signal will be. Maybe I already showed this to you. But if you plot f of u and v, you'll see that the signal peaks around well, I forget the value of u, but this is essentially the square, okay? So when all the momenta are of equal size, remember, then the interaction happens at a single time, so it's very efficient, but it's boring, just some power law. It's like accessing these irrelevant operators. Then, as I make u smaller, I'm dialing some hierarchy between the various modes, and I'm probing the particle production regime. And if I look here, there's no oscillation. I'm just getting some power loss, but it's coming from the zero modes. So the I epsilon prescription is really kicking in to generate this oscillatory profile. Okay? So that comes from careful analysis of the differential equation.
I just have one last question about this expansion. Just to appreciate what you're doing, we have to be careful to expand in some dimension less large quantity. Is that why you expand in m over h or something?
That's right, yeah. That's right. All right. Okay. Last thing I'll say is a bit about kinematics, which is related to these weight shifting operators. So it turns out that, so this is related kinematically, has the same kinematics, this 4-point function of the scalars is essentially related to the 4-point function of CFT primaries of specific dimension, delta j. In this case, delta equals 2, j equals 0 for our particular case. But we would like to compute generic exchanges and massless particles on the external legs. And then there are these weight shifting operators that come from conformal field theories. What they do, they're bilinear operators, W, say 1, 2. If you apply them to O1, delta 1, J1, O2, delta 2, J2, inside any correlation function, they will give you a correlation function compatible with kinematics, where the weights now are shifted. So the particular shifting depends on what you act on the outside. But for example, you could raise or lower the conformal dimension by 1 unit. You could raise or lower the spin by 1 unit. But it always acts in pairs. So the particular weight shifting operators that are available to you is some group theoretic story of how you compose various representations of the conformal group. So you draw Young tableau and blah blah blah. Okay, so then you classify the possibilities. So for example, you can raise both weights, or raise one weight, lower one weight, or raise one spin and lower one weight, and so on. So there are various possibilities. So it's a little bit of playing with Lego. So you have these blocks at your disposal, and you must apply them in a careful way to land in your desired spot. Okay? And you work a little bit harder, you can even show that you can raise the weights of the exchange lag. Even though the exchange lag doesn't appear explicitly in this correlator, you can show that you can also change the spin of the exchange lag. All this is to say that you don't need to work anymore in terms of dynamics. Once you solve one dynamical problem, all the other problems related to this type of exchange diagram are kinematical. Modulo this subtlety of adding spin on the external legs, which I can't do justice to it, but if you apply this naively, it looks like you're accomplished your goal, but there's still some subtle breaking of conformal symmetry that you must address if you have external spinning particles. Okay? From this first part of this last session, I hope I convinced you that these ideas, this set of ideas are useful. They're somewhat powerful, and the working horse of this business is the fact that you can trade these time integrals by a differential equation. Remember, I underline differential equation is like a master of this whole story, like controls everything that's going on. So after the break, I'm gonna, give a research talk essentially, telling you about where I think these differential equations come from. So the pedagogical part of the lectures ends here. Okay, so I hope it will be pedagogical, but maybe not. But I think it will be very exciting. It involves some very beautiful mathematics and so on. Okay, so let's take a break.